The ability to run on everything from Arduino boards to industrial controllers like the FX3U is what makes the OpenPLC so powerful. In this series, we will build our system using the ESP32S3 with an integrated LoRa chip. You can follow this series using any microcontroller board of your choice. However, we will be using this version of ESP32 because of its built-in LoRa radio support, which we will dive into in future videos. An IEC 61131 compliant PLC requires signal isolation, such as PC817 optocoupler modules for digital inputs and relay modules for digital outputs, and operates at 24 volts DC. For simplicity, we will begin by connecting push-button switches and LEDs directly to the ESP32. For today's demonstration, we will connect two push-button switches to GPIO2 and GPIO3 of the ESP32 and an LED to GPIO4. Regardless of the microcontroller used, all PLC IOs follow the IEC 61131-3 addressing format, which maps directly to hardware pins and internal memory locations. The PLC addresses follow a simple structure that tells us both where the data is located in memory and how large the data is, whether it is a single bit, a byte, a word, and a unique address. The percentage symbol is the IEC address prefix, and the memory locations can be I for input, Q for output, and M for internal memory. The data type or size can be X for digital input, output, or internal memory bit, B for byte, W for word or integer, D for double word or double integer, and L for long word or long integer. Thus, a digital input address is represented as shown, an output byte as, a memory word as. The same goes for the double word and long word. In OpenPLC, analog inputs and outputs are typically represented using word addresses. So for today's example, our PLC inputs and output will be mapped as shown. Now let's create a new project in the OpenPLC editor. I'll name the project Basic and create a folder with the same name. We will be working with ladder diagram and keep the default PLC cycle time set to 20 milliseconds. Now you can stay with the light or switch to dark mode from the display menu. Let me know in the comments which one you prefer. In the variable table, define button 1 and button 2 as Boolean, using their respective digital input addresses. Also define the LED as Boolean with the digital output address. Add a new rung in the program editor. Then drag two contacts and a coil from the sidebar, placing them in series to create a basic AND gate. To assign variables, begin typing the first letter of the variable name and choose the appropriate one from the drop-down list. You can also add a comment here to describe the function of the rung. Now let's start the simulation of this basic program using the sidebar icon. This will first compile the program for the simulator. Click on each contact and select Force Through to energize the coil. Click again to release the force. Stop the simulation, then drag the button 2 contact and place it below button 1 to form an OR gate. When you restart the simulation, forcing any of the contacts to true will activate the coil. Stop the simulation again. Move button 2 back to its original position. Double-click on it and select Negated to make it a normally closed contact. Place another contact below button 1 and assign it to the LED variable to implement the retaining contact logic. When you simulate, forcing bin 1 to true energizes the coil. Even after releasing the force, the LED coil remains energized. The coil will only de-energize when button 2 is forced true. This behavior is why it is called the retaining contact logic. Now let's delete this row and insert a new one. This time, drag the block icon onto the row. Double-clicking it will open the list of available function blocks. Expand the standard function blocks folder and select the SRO block. You can assign an execution order and enable additional control if needed. Function blocks are also accessible from the library window on the left-hand side. Place the button 1 contact at the S1 input of the block and the LED coil to its output. Then assign button 2 to the arrow input of the block. This implements a start-stop logic similar to the retaining contact logic, which can be observed in simulation mode. Now go to Device Configuration and select the ESP32 S3 or whichever board you are using. Ensure the board is connected to your computer and that the appropriate driver is installed. Click Refresh and select the correct communication port. Set the pins as previously defined, GPIO2 and GPIO3 for the button inputs, and GPIO4 for the LED output. Finally, compile the program and upload it to the ESP32. Once uploaded, pressing button 1 will turn on the LED, and pressing button 2 will turn it off. In the next video, we will take a closer look at timer functions in OpenPLC. You won't want to miss it. If this video helped you, hit subscribe, leave a comment and give it a thumbs up. See you in the next one.